Hey everybody, we're going to do an example of, so another infinite series. In this case, this one here, that's a 1, n equals 1 to, the sum from n equals 1 to infinity of 3 over n times n plus 3. So this one, there might be other ways to do it, but I'm going to do it as a telescoping series. This is just one way to look at this. So let's just go ahead and take a look. So first we could take, we're going to do partial fractions and write this as a over n plus b over n plus 3. And if we do our partial fractions, what do we get? A times n plus 3a plus bn. And if you work this out, we know that 3 times a, well, let's just write it out. We know that a plus b has to be 0, and that 3a has to equal 3. So a is equal to 1, and b equals negative 1, right? Which means that this whole fraction needs to be written as, can be written as 1 over n minus 1 over n plus 3. Okay, so there's our partial fractions work. Right, so that means our sum becomes the sum from n equals 1 to infinity of 1 over n minus 1 over n plus 3. All right, so the secret with a telescoping sum, I don't know if this is a secret, but a key is writing out the first few partial sums until you recognize a pattern, so you see how it's exactly going to, what each part, you'll end up with a form for the partial sums, right? You'll end up seeing what they're going to look like. So let's just do it. It'll be easier to explain as an example. So using this form, right, S1, the first partial sum, is just going to be 1 over 1 minus 1 over 4. S2, I'm going to have to start writing these smaller. 1 over 1 minus 1 over 4 plus 1 over 2 minus 1 over 5. S3 is going to be 1 over 1 minus 1 over 4 plus 1 over 2 minus 1 over 5 plus 1 over 3 minus 1 over 6. Let's do a couple more. 1 over 1 minus 1 over 4 plus 1 over 2 minus 1 over 5 plus 1 over 3 minus 1 over 6. Plus 1 over 4 minus 1 over 7. So we start to see a little bit of the pattern here, because what we're noticing, or what I'm noticing right now, is that this 1/4 cancels this 1/4. And now I'm starting to get an idea of what this thing's going to do exactly. Let's write out a couple more of them. So 1 over 1 minus 1 over 4 plus 1 over 2 minus 1 over 5 plus 1 over 3 minus 1 over 6 plus 1 over 4 minus 1 over 7, plus 1 over 5 minus 1 over 8. And again, in this case, I see that the 1/5 and the 1/4 cancel these terms back here. Okay. Let's do, I think one more should make this clear, maybe 2 more. Let's see what happens. 1 over 1 minus 1 over 4 plus 1 over 2 minus 1 over 5 plus 1 over 3 minus 1 over 6 plus 1 over 4 minus 1 over 7 plus 1 over 5 minus 1 over 8 plus 1 over 6 minus 1 over 9. So again, we're going to see 1/4, 1/5, 1/6, 4th, 1/5, 1/6, canceling, right? And this is just going to continue as I add the next. The next one I would add would have a plus 1/7, which would cancel the 1/7 there, and it would have a minus 1/10. So the next one would have a minus 1/8, a minus 1/9, and a minus 1/10 at the end, right? So what's going to happen is we're always going to cancel out all of these negative terms and all of the positive terms above 1/3, except for the last 3 negative terms. In other words, the nth partial sum. So now I'm going to start writing it with the, well, we'll do one more without, we'll still write the canceled fractions, and then I'll write it without them. So what we'll end up with, let's do it from, let's see, let's write the last three terms. So I'll have 1 over n minus 2. So this is the n minus 2 term, and it's going to have minus 1 over n minus 2 plus 3, or n plus 1, plus 1 over n minus 1 minus 1 over n plus 2, and I don't quite have enough room, plus 1 over n minus 1 over n plus 3. Okay. Now, all of these are going to cancel like they did above. And so this n minus 2 term, for instance, if we go backwards a few terms, some of the ones we haven't written, this is going to get canceled with something, this is going to get canceled with something, and this is going to go cancel with something. Just like this last term's positive term got canceled, this last positive term got canceled, this last positive term got canceled, this last positive term is going to get canceled. And so all that's going to be left, we can write this out as, we've got 1 plus 1/2 plus 1/3 minus, we've got 1 over n plus 1 minus 1 over n plus 2 minus 1 over n plus 3. Okay, so that looks like our, this looks like a nice easy form for writing out this sum, right? We can simplify this. We've got 6/6, 3/6, and 2/6. So what did I just say? Oh, 11/6 minus 1 over n plus 1 minus 1 over n plus 2 minus 1 over n plus 3, right? So then the last step is we can take the limit of this. Remember, the definition of an infinite sum, if it exists, is the limit of the partial sums. Every partial sum looks like this once we get past S6, it looks like, right? So the limit as n goes to infinity of S sub n, or the limit as n goes to infinity of 11/6 minus 1 over n plus 1 minus 1 over n plus 2 minus 1 over n plus 3, right? Well, the limit of a constant, n changing doesn't change what this number is. Each of these goes to 0. We've got n in the denominator getting larger and larger, so the limit is just 11/6, okay? So that's a nice example of a telescoping sum. This is a tricky one. There's this sort of, there was this disconnect. The telescoping part, the part where they cancel each other, was separated by 3 terms, which sometimes makes it difficult to exactly see what's happening. If you're not convinced of this, write out a few more, write S7, S8, S9, and see what happens, and you'll see that this form that I wrote here is always true, right? Let's convince ourselves one more way. I'm going to open up Desmos. I think Desmos is nice for this. There might be other online stuff, but this is the one I'm familiar with. I actually don't need the graphing part. I'm just going to use the calculator part. So I'm going to write in, and this is a nice thing for us to know. They have a nice, I just typed sum. And of course, we can't go up to infinity. I'm going to do it up to k, and I'm going to write our expression, 1 divided by n. Actually, let's write it in the original. It was 3 divided by n over n plus 3. Right, and notice they give me the option for the slider. What I'm going to do is change how high we go. And I want to go from 1. Let's go up to 100 steps by 1, right? And what we think is going to happen is that this sum should be getting closer and closer to 11/6. And since it's going to give me these answers as decimals, I want to know that it's 1.83 repeater, right? So right now, just so if you're not as familiar with Desmos, I've told it to add up n equals 1 to k for this expression, and right now k is equal to 1, and I can change k. So when I do, here's our second partial sum. right? So when k equals 1, it's 0.75. If you look back, that's the same thing we got for the first partial sum. And as I increase the number of terms I'm going to, right, we can see this decimal slowly climbing, right? And this is not going to prove to us that it's getting there. Maybe we need to go a little higher. Let's try going up to, I don't know, 10,000 steps. So now I'm up to the 5,800th sum, and I'm at 1.83, and then some stuff that's a little smaller. Notice it's getting even closer now, right? 1.833. Let's add a couple zeros. Let's see how high this thing will compute. So, right, you can see now adding another, what did I do? A factor of 100, made it 100 times more sums, and we're adding 3. So apparently it grows pretty slowly. It takes a while to get up there, but it is at least not intuitively, but there's some evidence here, right? It's not convincing me that I'm wrong, and it certainly seems like it's going to this, which supports the work we did here. So this is a nice tool to use. I mean, there's other ones out there, but this is the one I like. You know, getting your sense of these things, this can really help to understand what's happening here, right? We can get a look at these partial sums. Okay, so that's it for this one. Thanks, everybody. I'll see you next time.